All right, our final talk in this session is by Alcesta Scalas, and the paper is Less is More, Multiparty Session Types Revisited.
The multi-party session types theory. So we'll start with an overview and some examples. So the multi-party session types framework is about verifying message passing programs via types. And the idea that we've seen from the previous speakers too is to describe multi-party protocols as global types that describe how multiple roles should exchange messages. Then the global type is projected into a set of local types, each one describing how each role is supposed to send and receive messages. And these local types are used to type check implementations. This framework has been developed in many directions in the last decade. So for example, consider this small protocol with three roles. There is a server, a client, and an authentication provider. And in this global type, the server is sending to the client either a login message or a cancel message. Login means that the client must log in, so the client is supposed to send to the authenticator a password message carrying a string, and then the authenticator will notify the server whether the authentication was successful with a Boolean. And then here the session ends, but it can continue. This is for simplicity. Otherwise, if the server tells the client to just cancel the interaction, then the client notifies the authenticator with a quit message and the session ends. So in the multi-party session types framework, you can project this global type into each role, for instance, the server, and you get this local type that says that the server is supposed to send to the client, this O plus must send either login or cancel, and then if it chooses login, then it must wait to receive an out message carrying a Boolean from the authenticator. Otherwise, if it sends cancel, nothing happens. The session just ends. And with this type, you can type check a process that implements this type by essentially playing the role of S in a session. And you can repeat for each role in the protocol, and with these types, you can independently type check the implementations of the client and the service, the authenticator. So once you have all of this, you can, for instance, compose the processes so they can interact, and you can verify that the composition is type safe. So you can take, for instance, these implementations that are correct. I will not go into details. And you can verify if you type check it with the ensemble of all the local types, the type checking succeeds. And then you may expect that since this is well typed, if it enjoys subject reduction. So if it reduces by interacting, then the reduct P prime here, if you go from P to P prime, then also the process you reach is also typed, so it's type safe. But if you're familiar with the type systems for process calculus, you may expect that there is some set condition. And in many classical work on session types, this set condition is called consistency, and it is applied on typing contexts and requires the typing context, so this set of types to be consistent. And in this small example, this protocol, this multi-party protocol, does not yield a consistent typing context. Therefore, we cannot prove that this implementation or any implementation is type safe, even if it is correct. So in this talk, in this work, we address the problem with a new take on the whole theory, and we claim that our theory is less complicated, more powerful than the classical one, in the sense it's less complicated because it does not require this consistency clause, it does not even require global types, I will show how, and it's more powerful in the sense that types more processes, subsumes the classic results in a more general setting, and it even opens a door to blending type checking and model checking. And we have also an artifact that has been, that is available. So in this talk now, I will explain what is the gist of the problem we are facing with in our example. So consider this smaller example where we have this step in judgment that says that there are two rows, A and B. A is going to send to B a message carrying a string, and then it's waiting to receive a reply carrying an integer, while B is expecting a message from A carrying an integer, and then will send a reply. Now, if we admit this step in judgment, then we can write a process that types like this one, that, for instance, is where we have A sends to B hi, and then waits for a reply, while B receives X, but it expects it to be an integer. So it tries to reply to A by sending X plus 1. And you can imagine that if you actually run this process, even if it's well typed, then this hi message goes to X, and then you get this configuration where you get hi plus 1. And this is, of course, ill-typed. So you don't want to accept this type in judgment. You need a criterion to reject it. And there is a well-known criterion in the binary session type setting. It is called duality. That's, okay, first I need to say a few more things. The criterion you want to use to reject this example must be also well-behaved, in the sense that it must be preserved when process is reduced, of course, and also it must survive when you have to split the typing context to type parallel compositions. So things get a bit technical, but that's what you want. And again, in the binary session types theory, this criterion satisfying all these conditions is called duality. The gist is, if you have a role in a binary session that is sending a message and then waiting for a reply, it's dual, so the other role should expect a message and then send a reply. And so you see there are the same messages in the same order, but you flip inputs and outputs, and you have compatible payloads. A string here is a string here. And this is the problem in this example. Here, one is sending a string, the other is expecting an integer. So duality allows to rule out this case. But what happens if we have more than two rows? Well, there are many works. The classical approach in multiparty session types is to extend duality as consistency. And I will give an intuition based on our example. So the idea is that you take the local types of your multiparty protocol, and then you observe how each pair of rows is willing to interact. For instance, in our authentication example, you can observe how the service is willing to interact with the client, and with this operator, you see that it's willing to either send, login, or cancel. You do the same to see how the client is willing to interact with the service, and you see that it's willing to receive either login or cancel. These two are dual, so this check succeeds. But if you continue the check, and for instance check how the authenticator is wishing to interact with the service, then you get something odd. So you see that the authenticator may either send an auth message or nothing. And this cannot be expressed as a session type. This means that one of the so-called partial projections of these types is undefined, therefore the consistency check fails. So this is why our small example is rejected. So consistency is quite subtle and quite limiting because it creates problems when there are inter-role dependencies inside the protocol, when there is recursion. It has been overlooked in some previous works. In the paper, we give more details about it. There is one alternative, that is, you can formalize your type safety based on the existence of a global type that projects into a set of local types that form your typing context. You can use this invariant instead, and it's developed, for instance, in these papers. And there are some pros. For instance, then you can support our small example, but then the theory becomes quite complicated because then now you have a lot of moving parts in your statements and proofs. In particular, you need to give a global type semantics and handle the projections. It becomes quite complicated. And also, in a way, you are limited by the language you choose for global types and projections and how expressive they are. So can we do something a bit simpler? So what we did is go for a radical simplification. So we essentially redid the proofs of the session types theory by assuming a much weaker typing context safety invariant, and without assuming that, to have consistency, duality, not even global types. So the gist is we have a typing judgment that says that P is well typed in a given a set of local types when the set of the typing context, the local types are safe. Where safe essentially means that whenever two types for rows A and B are wishing to interact in the typing context, it must be the case that all the outputs from A to B are a subset of the inputs provided by B towards A. And also the payloads must be compatible via subtyping. And whenever the typing context reduces with its semantics by mimicking essentially the process reductions, the safety invariant is preserved. Actually, we do one more step because we formalize this revised framework by making the safety invariant parametric itself. So you can instantiate the safety invariant with any property that guarantees these two desiderata I described. And why do we do that? Well, the idea is that by fine-tuning the property, you can get more properties for typed processes. So this is a design that is inspired by the generic type system for the pi calculus by Igarashi and Kobayashi. The idea is that consider the set of all the typing contexts that you may have that describe many possible protocols, and it also contains, for instance, our example. Well, if you want to guarantee that a typed process is type safe, you can instantiate the parameter phi to check that the typing context, the type P, is safe. So this is the largest safety property according to our definition. This is enough for type safety. But then you may want more. So for instance, you may want P to be deadlock free. So what you can do in this case, you can instantiate the invariant phi as the deadlock freedom, so this property here, and then you reduce the set of allowed typing contexts and protocols you support, and now you know if gamma is deadlock free, also the process is deadlock free. Or you may want your process to be live. Each pending input will always eventually receive some input. And then what you can do is restrict phi to live, so check that the typing context is live. This is described in the paper. Or you may want P to be terminating, and then you instantiate phi as terminating, and so on and so forth. So by restricting the property, you enforce the behavior of typed processes. And in this set, there is also the classic theory that says more or less here. So this includes all consistent typing contexts that are safe, and all global types that project a typing context that yield a live protocol. So our theory only uses local types and yet supports all the classic theory and more around it. So one question may be, okay, but how do you actually check your new typing judgment? Because now you have to check both this syntactic judgment and also this more semantic, let's say, possibly semantic property of gamma. Well, the syntactic part of the judgment is decidable because it's very, very close to the classic one. We really do minimal changes on purpose to be compatible with the old theory. And we also show many ways that you can use to instantiate phi so that it's decidable. So when you have your set of possible typing contexts, you can, from the previous slide, still use the classic theory. So you can use syntactic methods to check gamma via projection or consistency. But these are just special cases of the more overall semantic framework where you can also check properties like safe, deadlock freedom, liveness, and they are all decidable. And the nice thing is that if you use these semantic properties of gamma, then it opens a natural door to model checking because you can express these properties as a new calculus formula and then use a model checker to verify them. And indeed, this is what we do in our artifact that is available together with the paper. So we developed a tool that is called the Multiparty Session Types Toolkit, MPST. And what it does, it allows users to describe multi-party protocols, either as global types or local types. And then the tool will translate them into a process calculus that the MCLR2 model checker understands. And then it will verify whether various properties that we support, like safety, degree of freedom, liveness, and so on, it will check whether they hold or not. And so this shows that the approach is feasible. We have some measurements in the paper that are pretty encouraging. Essentially, we can check many properties on not so small systems in around 1 second. And then we discover that with the latest version of MCLR2, using a different solver, the performance is 10 times better. But anyway, the approach looks definitely viable, and the tool is available if you want to try. So this is it. What we presented in this work is a new theory for multiparty session types that we claim is less complicated and more powerful than the classic one. Less complicated because it does not have consistency restrictions. It does not require you to use global types. You can if you want. They are supported inside the framework essentially as a special case. It does not require projections and so on. And yet it's more powerful than the classic one because it supports everything that the old theory did. It also fixes some flaws in previous works that were based on some overlooking of the consistency restrictions, supports many more protocols, allows to open a door to combine type checking and model checking. And by the way, it also supports asynchronous sessions. I could not talk about it during this presentation, but it was a crucial design during our work. We wanted to extend to both to synchronous and asynchronous session types. And you can see the paper for more. And if you want to try our artifact, it's available. Please try it.
Okay, we have time for questions. I'll start with one from Slido. I mean, the person has literally said, "What kinds of interesting and decidable phi have you used?"
Undecidable.
Or interesting and decidable.
And decidable. So, well, the ones listed in the paper, we have safety, that is the basic one, that at least guarantees your process will not have runtime errors. And then there's degree of freedom, that guarantees that at least part of the multi-party protocol will always be running. And liveness in different variants that essentially handle fairness differently. Allows to ensure that if you have a multi-party protocol and some role is waiting for an input, the input will always eventually arrive. So some other role will be willing to interact at some point. And all these properties are decidable. So.
Okay. So, I mean, I have a question. I mean, what are the implications for people using tools that have been built on top of multi-party session types? Like, for example, Scribble, I think, is built on top. I mean, does this mean that Scribble needs to be changed?
Well, Scribble does not implement the theory directly. It's like essentially comes out of the theory of multi-party session types.
Okay.
And this essentially shows that the foundations are solid, even if when they go a bit beyond the theory, because the Scribble is also oriented towards practical uses. So sometimes it implements things that are not always fully formalized. And also it gives rooms for more applications. I mean, the reason we made another tool is that now we can reason on multi-party interactions, both assuming to have a global type that is the starting point of Scribble. Mm-hmm. It starts from the presence of a global type, or even if we don't have it. We just have an ensemble of local types describing the behavior of multiple components. We are willing to check whether they are compatible, and we can use then this approach to see whether the composition is safe, is live, and so on, is degree-free. And then if it's true, then we can use them to type processes and verify them. So the Scribble could be extended also in that direction in principle.
Okay. Do we have any questions? We do. Phil, we need to record this, so use the microphone.
Apologies if this is a silly question, but for size of states ranging from 37 to 440,000, it always uses just about 1 second. Why is that?
It's due to the solver we were using. We tried this one. It had good performance, and we were satisfied. But after we noticed that if you use another solver, the numbers are very different and much lower. So I guess we should ask to the authors of MSLR2. This solver always seems to take roughly 1 second. I don't know why. But if here you use PDF solve, if you are familiar with MSLR2, you get much different numbers that are more proportional to the number of states, but they are like in the order of 0.05 seconds.
You should just delete the wait 1 second instruction from the solver.
I had a look at the code. I was wondering, but I'm not.
A very different question. How does this talk relate to the previous talk? Can you put them together?
Well, what we address in the paper is, let's say, the bare bones theory of multiparty session types, because we wanted to focus on what we change. And I believe that all the extensions built on multiparty session types so far can also be built on this new take. I don't see why not. Maybe the more philosophical approach is that this revision of the theory is, let me go back, goes more in both directions. So while the classic framework goes mainly from top to bottom, so you have a global type, and then you go down to local views and to type checking. Our theory also works if you have a set of local types, and you want to verify whether they are correct, even if you don't have a top-down approach to a system. And so with this approach, probably the results are more natural to be developed at the level of local types in a more semantic way. So for instance, an extension with dynamic roles. And then you can also develop a language for global types that gives you a way to write them in a maybe more user-friendly way, and is a special case of the semantic characterization of your new extension. So, but this is...
This I should answer. So, scribble implementation, we use not only just to describe and project, but we are checking many kind of well-formedness checking. With this approach, if we can integrate, actually some part of our implementation using model checking tool. So this approach, we can even writing script, we can weakening the well-formedness check more generalized, and so that we can integrate with this approach. So that is also good practical integration.
One last question.
I guess this is very much related to the others. You still insist on global types, right? But it's not always true that you can build a global type from the types that you have. Am I right?
No, in this, okay.
You don't even have a syntax for global types in this case, no projection, no nothing, yeah? But
so in the paper, what we did is we took the common syntax for global types, and we showed that if you use them, essentially you end up here in what we support. So you always get protocols that are live, but for the theory, you don't need that.
So why the multi-party name in the title?
Well, because we have protocols with multiple parties. But we are more, let's say, bottom-up than top-down, probably. It's a different take, but we support the classic approach, too. So.
Okay, we're going to end the session. Do remember that there'll be a talk from Tom Ball at 6 o'clock, and let's thank our speaker.